we are going to be talking today about the simulating of economics of autonomous haulage mining trucks. I'm Andrey Malykhanov. I'm CEO of Amalgama Software Design, and Jaco-Ben Vosloo is with me. Amalgama Software Design, that's the company behind the MineTwin tool. So here's my email over here. I have some experience in simulation. I started with building simulation models in Haulage, then we switched over to more domain-specific tools, and now we're doing this domain-specific mining simulations with MineTwin. And I will let Jaco-Ben introduce himself.
Hi everyone, I'm Jaco-Ben Vosloo, or JB for short. So I'm a simulation specialist, been working with MineTwin for the last 4 years, but associated with other simulation and consulting companies as well. Got a lot of supply chain, production and mining simulation experience, also some practical industry experience, worked with BHP Billiton and some of their mines and their smelters as well. So our agenda for today is we're going to first start off and give you an overview of the stakeholders that was involved in this project. Then we're going to have a bit of a project background and show you exactly the question that we tried to answer, the original question and what the simulation was going to do for this project. We're going to look a bit at a high level about the open pit mine haulage system, what parts were in scope and out of scope, what we modeled. Then we're going to have a look at the simulation study design. We're also going to do a very brief model demonstration of MineTwin. We're not going to focus much on the tool itself, just on the parts that was used for this specific study. So it's going to be very brief. We're going to look at the optimal fleet composition analysis, because that we'll see is the biggest thing here is like, what is the optimal fleet for this specific question when you've got manned vehicles and you're moving them to autonomous. We're also going to look at the impact that pit depth has on this question, the answer that you get out of this, and specifically the net present value or NPV results from this whole study. And then we're going to do a brief overview, if there's still some time, of the benefits of using MineTwin compared to industry standard and general simulation tools. So a little bit of a background about the project. So it originally started with Pronto AI. They deliver off-road autonomous haulage systems, or AHS, and they specifically focus on rugged environments, specific industrial environments as well as mining environments, and also specifically in small vehicles. They managed to bring the cost down of automating a small autonomous, a small truck and other equipment significantly compared to bigger trucks. And they wanted a research study to test the financial and operational impacts of in mining moving from big manned trucks to smaller autonomous vehicles. And if you want to learn more about them, you've got their website linked there. And they approached Whittle Consulting to do this study for them. Now, Whittle has this integrated strategic planning, which is an approach that they've used for long-term mine planning, and it considers all parts of the value chain, everything from inputs back into the community to what is your mining rates, to what is the life of mine, to how your pit shell should be designed, how many shells should you have, etc. But for this specific study, because it's kind of new and there's no information available about exactly what the number of trucks or excavators is for specific setups, they required a detailed simulation to accurately calculate the NPV for the research study. And if you want to learn more about them, you can visit their website as well. And then Whittle contacted us and said, we need a detailed discrete event simulation modeling tool so that we can test all our assumptions and we can find the optimum fleet configuration. Now, MineTwin is able to simulate both open pit and underground mines, and we provided them with a tool to do this sensitivity analysis and provide the optimum, or the ranges for the truck and loader configurations for various stages in the life of mine. So I'll hand over to Andrey to talk a little bit more about the background of the project.
Yeah, so what is the object of interest or system of interest? It's actually, we were asked to compare medium manned versus small autonomous trucks. So when I say medium, it's actually quite a big thing. So it's a Caterpillar that can carry up to 100 tons, and it's typically paired with that type of model of excavator, and it's manned. What is small autonomous trucks is it's still quite big, right? It's small relative to the other mining machines. It's 40-ton Scania that have been chosen to be paired with this Hitachi shovel that's autonomous. That's actually the type of trucks that Pronto guys can automate. Obviously, there's trade-offs that we needed to resolve with the simulation somehow. So, industry have historically chosen to use the bigger trucks in the mine. Obviously, there's 450 tons in the trucks in the mine, in some mines, but the bigger the truck, the more efficient the transportation is, the more there is the fraction of the ore that you are hauling upwards as compared to the mass of the truck itself, the mass of its fuel, etc. So obviously there's less congestion, as there's less moving parts, less probability of congestion, but the negative factors here are human factor delays because they are manned, all sorts of human factors, we factor that in. Uneven truck speed, that's a serious problem. That's not very evident on the surface, but all the manned trucks actually drive with the different speeds, and if they queue or if they swarm one after the other, they all arrive to the dumping point at the same time. There's additional queuing because of this, and obviously the greater impact of a single unit failures. So these trucks are designed to be very reliable because the bigger the truck, the more the impact of its failure. So uniform speed on the other side, right? If we automate the trucks, be it a large truck or a small truck, we get more uniform speed, probably less queuing, less human factors, delays, but we need more excavators because, as you notice there, we need smaller shovels, so we need to buy more of them. How much more, we'll see very soon. And there's going to be presumably more congestion because there's a lot more moving parts. And statistically speaking, there must be more congestion, more queuing in front of excavators, in front of dumping points elsewhere. And then expenses for autonomous equipment, etc. So this has to be considered during the NPV calculation as well. So we use the simulation to actually resolve this trade-off and determine which is the best option. So open pit mine haulage system, how it looks like. The very bottom part that looks like a grid, there's actually a grid of blocks where the ore is being excavated. The trucks, the excavators scoop the ore and put it on the trucks. They travel further upwards. The typical grade is 5 to 6 to 7%, and they travel to one of the destinations, depending on what they mine. It can be a waste storage stockpile or crusher, and obviously this is the flow of the ore. And what we are interested in simulating is trucks queuing at unloading points, planned and unplanned stoppages. Of course, in autonomous case, there must be less stoppages due to human factors, less shift breaks, etc. Then trucks queuing at excavators, the biggest problem in mining probably. Excavators waiting for trucks, that's the opposite problem. You'll see very soon what the analysis behind this is. And then trucks swarming somewhere here. So these are all the effects that we needed to simulate. So what was the design of our simulation study? We took a sample ore body together with Whittle Consulting guys, with drill and blast open pit mining technology, typical North American setting, copper style ore body. We took the three destinations: stockpile, crusher, and waste storage. It can be sometimes 2 destinations, but we took the setup with 3. We considered 3 stages of mining. The beginning stage where the pit is quite shallow, the medium pit stage, and the deep pit stage. The depths are here in the meters. So for every stage we fixed the haulage rate. So we just solved, we used the Jaco-Ben software to calculate this economically optimal haulage rate, tons moved per day. We fixed that, and we ran experiments in MineTwin to calculate the required number of trucks and excavators to reach that same haulage rate for every case. And we had several cases, like 4 fleet times, which is 100 tons, 40 tons, X manned and autonomous. That gave us 4 fleet configurations. We ran them for all the 3 stages. We varied for every combination of fleet type and stage. We varied number of trucks and excavators. Obviously, applied some replications to find the required number of trucks and excavators to sustain that haulage rate. Then we externally took the results of the simulation of MineTwin and calculated NPV in Excel, because obviously Excel is probably still the best tool for economic models. So we factored in factors like capex, or prices, rock movements, etc. So let me hand over to Jaco-Ben.
So this is the editor view of MineTwin. So on the left-hand side, you can see all the data that we read in from a scenario file. The scenario file is just an Excel file. You don't need to go and change anything in the Excel file. It's just the format that we chose for our scenario. Everything is data-driven in here. Everything from the routes, which you get either from a DXF file or a DESWIG file, or you can draw it in manually, all the block data, all the material, all the equipment gets set up in here. So it is the same MineTwin tool that you will use to simulate any kind of open pit or underground mine. So in the editor view, you get to make all these changes. Once you're ready, you hit the play button, and now the simulation gets created. There's a scheduler that runs that assigns equipment to different locations. You'll see those yellow parts there are blocks. You can see the excavators going to these blocks, starting to excavate, a truck going up to it, being loaded. Here in the view here at the bottom, we've got Gantt charts that in detail tell you what every piece of equipment that you've selected has been doing, or it's planned to do based on the scheduler's algorithm, or that it is currently doing. Literally, it started at 0 to 48, it excavated for 6 minutes, loaded into that specific truck. Then you can also view this for every other piece of equipment. So if we look at the trucks, we can see the stacked state charts for how much time they spent in each state. We can click on pretty much anything inside the application to view their current status. There's also a nice 3D view, and here we imported the geometries, the surfaces, so you can get a better visual view of what is exactly happening in your model. So that's really nice for verification and validation. If the client, or in this case like Whittle Consulting, wants to make sure that the way that we are mining, does it make sense? Like, are we mining the benches in the right order? Is it valid what we're simulating? Right? So you really need that 3D view so that it can be verified and validated. The next video is just showing you a little bit more detail about how deep you can go into this. On every single piece of equipment, you can click on it, and it will tell you what it is currently busy with. So this top one is loading, that one is moving to loading, moving to unloading. It tells you how much tons it's carrying, what's the availability, what's the utilization. You can fix these little pop-ups, and then the line follows the equipment, or you can follow the equipment by default. So there's really an intense amount of detail that is available for you in the UI that you can use to make predictions, to analyze your current situation, etc. But when we get to actually running those over 900 different experiments and applications that Andrey was talking about, you can't run it in this environment, it's going to take forever. Right? So there we set up some batch runs on our server, and we eventually get the massive text file or an Excel file with all the replications and averages, and we analyzed it. And now we need to make a decision on what is the optimal fleet composition for each one of the slices of time that we simulated for the life of mine. So the first one we're going to look at here is a very shallow part of the mine, so it's in the initial phases of the life of mine. What you see here on the x-axis is the number of trucks. So we keep on adding trucks And then we have a look at what is the effective utilization of the excavators in the blue versus the trucks in the orange. So the effective utilization is the utilized time that the equipment was spending doing useful work. So a truck is still utilized if it is waiting in the queue for other trucks to finish dumping, or it's waiting for the excavator to load it, right? Effective utilization is actually the being loaded, moving to unloading, unloading, moving back to loading, etc. So what we see here is as we are adding more trucks, the excavators get utilized more effectively, right? So in the beginning, when there's not enough trucks, we are starving the excavator. It's ready to load material, but there's no trucks. And here in this beginning stages, we are utilizing the trucks as much as possible, right? They're just constantly going from loading area to dump area. Then at some stage, there's a crossover point where adding in more trucks, you just decrease the average effective utilization of each truck. Because you're adding in more trucks, but now it just spends its time waiting in the queue. And you're adding more trucks, but the excavators can't be more busy than 90% because there's some unavailability, there's off-schedule periods, etc. So you get this peak, like adding more trucks doesn't benefit the system. So this is interesting, and we can say, Andrey will dive a little bit deeper into exactly how we made that decision, but you can see from about 30 to 35 trucks, for this specific scenario, for this specific situation, you had very good effective utilization across both your excavators and trucks, right? But it's still a hard decision to make. You can sometimes reach the same target tons with adding more trucks or adding one more excavator. So it becomes really complex. What makes this even more complex, and why life of mine planning and fleet management and replacement of your vehicles is such an important thing that you must, why it's so important to use simulation, is because when you move to a deeper part of the bit, so this is now stage A2, suddenly the chart looks completely different. Now, we only start not starving or not benefiting from adding additional trucks around 60 trucks. And it makes kind of sense. We've extended the distance from the dumping area all the way down into the pit. So we essentially have a longer pipe to fill with trucks to make sure that we do not starve the excavator, right? So in the beginning of the life of mine, we will get by with like 30, 35 trucks, and in that case, 5 excavators. But towards the deeper part of the pit, we actually need to have more trucks to make sure we do not starve the excavators. And this is just 2 of the depths that we actually simulate.
So we can look at the same basically data from a little bit different perspective. So that's a different type of diagram which shows conceptually the same, that presents conceptually the same data, but shows what exactly did we do within this study to achieve the goals of this study. So in the cells here, there is a sum of effective utilizations, average effective utilizations of trucks and excavators. Obviously, the maximum, theoretical maximum was 200%. The greener the cell is, the more effectively we are using our fleet of trucks and excavators. So green is good. And you can see here, so we are good. We are able to use quite effectively our fleet if we have just 20 trucks and 4 excavators. So we'll be good in utilization-wise. But ton-wise, we will not be reaching our target. Remember about those fixed haulage rates that we compared ourselves against. So, and the haulage rate, obviously there's a haulage rate associated with every cell. Here I just put this green frame to highlight the cases where we were able to reach our target haulage rate. So this is to say, with 45 trucks and 9 excavators utilized quite efficiently, we are able to use our haulage rate. And this blue one shows the area where we exceeded the haulage rate. We don't need these cases because we want to compare apples with apples. So we did this analysis for small autonomous trucks, which this picture shows, and the big trucks as well. But here, the second picture is the same small autonomous trucks, but the deeper pit. So we now went deeper into the pit, so the haulage distance is longer, and it's probably less available dumping points because we start to haul more ore, and all of the ore typically gets to crusher, and crusher is a very small thing. There's just a certain amount of trucks that can offload simultaneously at the crusher, and you can see the picture changed. Basically, we have become more trucks constrained, or put in simpler words, each excavator now needs more trucks to be efficiently utilized. And here again, we determined that we are able to reach the haulage rate that we were targeting for with 75 trucks and 8 excavators. That's actually the final result of our calculation. We used the simulation to determine the equivalent truck fleet sizes of manned versus autonomous, big versus small trucks. And as I told you earlier, we took it offline and calculated the NPV of the mine, assuming all financials in Excel. So we came to some calculation of the NPV of the mine in $1 million, whatever, for manned medium trucks. That was our base case. That is the NPV that we calculated for autonomous medium trucks, like the larger trucks, but autonomous. You can see it's quite bigger. But what we took here for the calculation is the standard vendor price from Caterpillar for automating these big trucks, which is quite big. I mean, the price was quite big. So manned small trucks, obviously industry chooses bigger trucks for a reason. Then autonomous small trucks, the NPV-wise, we are much better because, like 29% better, because automating the small trucks is much cheaper with the technology of this Pronto AI. Guys, operations-wise, having autonomous bigger trucks is more beneficial. But when we factor the costs into that calculation, that's the result that we get. I will hand over to Jaco-Ben to talk about the data issues.
So we've got the answer now, and the question is how confident are we in the answer? So there's a couple of decision support approaches that's available for us in mining, and the first one is just static calculations, right? In Excel, you just go, well, what's the average cycle time for a truck to a loader? Okay, I'm not exactly sure how it changes if we've got more loaders, less loaders, more excavators, less excavators, shallow pit, deep pit, etc. So we have to use some averages, average distances, durations, load sizes, etc. And unless you invest a significant amount of time, there's no time factor in your model, right? Maybe you create multiple columns and every 5 minutes is a column. So that is just a high-level calculation that you can do. Now, there exist semi-dynamic calculations and some industry standard tools here, but most of them only simulate the excavation part. And they've got approximation of trucks to shovels, so you allocate your shovels to specific locations in the mine, you allocate your trucks, and it simulates kind of the same distances throughout the simulation period. And it does not consider drilling, blasting, excavator relocation, etc. Now, if you go to the far end of the scale, you've got a full-scale simulation, and this can consider your queuing in front of excavators, the dumping points. You simulate the daily allocations of trucks by excavators, you simulate unplanned and planned breakdowns, drilling, blasting, etc. And if you move from the top to the bottom, you obviously require a lot more detail to input into the model, but you also get way more confidence in your answer, right? So you're able to simulate and take care of more aspects of the mine if you move down to full-scale simulation.
Yeah, so probably the last meaningful slide is now we kind of realize that we need to do the simulation, but what are the options here? Basically, there are 3 options. The first one is using industry standard haulage simulation tools. There's a couple of them. And the other end of this, of using simulation, of building simulation, is using general purpose simulation tools like Haulage, Simio, whatever. And somewhere in the middle there is this MineTwin tool, which we are kind of presenting here. So the quick discussion of advantages and disadvantages of each approach. We believe that it takes the best from two worlds. Obviously, we're a little bit biased. As standard tools from the industry, MineTwin has inbuilt standard mining processes, objects, and reports. It has also a library of standard equipment types and models with typical characteristics. Of course, they need to be validated from case to case. And obviously, ability to import geometric and geological data from industry standard formats like TESVIC or Micromine, whatever. From general purpose tool, we take ability to implement scheduling and coordination logic and customize it with code. There is a basic scheduling logic, which is good enough for some cases. For the other, you can use Java code to specify the details of this logic, and the ability to add custom objects and processes, which is not possible in industry standard tools, but here in MineTwin, you can do pretty much the same what you can do in any logic, with the difference that you have to code in Java as opposed to drag and drop and code from time to time. So that concludes our presentation, I think. Thank you, Jaco-Ben. And here's some links. You can use the QR code. And here's a link to this Whittle Consulting report. There's a big paper there, and that was somewhat informed by the simulation, but it contains a lot of other sections if you are curious. So I think we're open to questions.
Andrey, what was your assumptions regarding OPEX and CAPEX? When I served on the advisory board for BHP at the time, the big downside of the autonomous vehicles was that there was going to be a 1-to-1 and maybe even a 1-to-2 increase from drivers to maintenance crews, because the autonomous was still very unreliable and often had to be removed off-site to get maintenance done, etc. What was your assumption?
The maintenance intervals were longer from the operational standpoint. The maintenance prices or repair prices for autonomous equipment were provided by that vendor, that Pronto AI vendor, and the Caterpillar as well. So we just took those numbers into this NPV calculations. But if these assumptions change, we can still reuse our simulation results because we just simulated the physics, not the economics. The economics were done fully out of the simulation in the Whittle Consulting's cost model.
But in general, your assumption is that maintenance on the autonomous will go down?
No. There will be...
Yeah, the maintenance stays the same, and we just added small additional maintenance where they think this would be, they would have to maintain that equipment, the automation equipment, outside of the standard maintenance cycle. So the availability changed by like less than 1%. But the cost is something that is completely outside.
This is one of the nicest simulation talks I've heard at the conference so far, so good job. A quick comment and then a question. Comment is, it seems to me that this is just really set up to be a move to the digital twin level, and so I think that's a nice next step. The question is, these are autonomous vehicles. Does that mean that there's no interaction, or do they actually get loaded up, somebody hits a button and then off they go?
No, they are fully autonomous. They sense the excavator, they sense the event when the excavator finishes loading them, and then they go. They are coordinating between each other. And there's like pre-assigned routes to them, and the roads where they operate are fenced to some extent. But the innovation from this Pronto guys is they provided some safety mechanisms with lidars, I think, that can allow to operate these trucks together with manned vehicles. Like if there's a manned service vehicles, it can be allowed to drive the same paths with these autonomous things.
Thank you.
All right, well, let's give it up for them one more time. Thank you, guys.
Thank you so much for watching. If you are curious and want to learn to know more, please contact us, use the links in the description, or download your free copy of MineTwin today. Until next time, thank you.